Hello, I'm MichaelWeylandt. I'm a PhD student at the Department of Statistics at Rice, down in Texas, the place that flooded recently. This is just it's not even so much a talk, it's sort of a talk about a talk on how to do hidden Markov models with Stan. So let's get into it. Okay, so full disclosure, most of this work is not actually mine. This was done by a student I've worked with who couldn't make it. Luis Damiano, he's fantastic. He knows a lot of finance, knows a lot of statistics, is applying to PhD programs as we speak. So if anybody's looking for somebody who knows this stuff really well, do talk to me after and I'll put you in touch with him. So credit where credit's due. Where did this talk really actually come from? This, like most things, came from a blog post. This is Bob's, right? Saying, just sort of acknowledging that there's this confusion about whether these sort of hidden Markov models can even be done in Stan. Yes, they can. Bob says that very nicely here. Bob says more. I guess it got cut off the bottom of the slide. And so this is really just sort of talking about that. So again, this is more of a public service announcement that these things can be done. There's not a huge amount of novelty here. It's more just a plug for a really useful way to think about things and model things. So hidden Markov models, what are they? Like most things, these come better in an example. So who has seen this chart? There are dates along the bottom, if that appeals anything. Everybody knows what this is? S&P 500, but yeah, right. This is the stock market, essentially. How about this one? Finance people know what this one is?
Return.
Yeah, this is just the day-over-day change, right? This is probably more meaningful because it's actually what happened at each point. This is what most of the time you actually spend your time trying to model in finance. How about this one? Recession, right? So what is this? This is the NBER recession indicator. This is basically a bunch of economists get together in a room and they think really, really hard and they say there was a recession 4 years ago. Glad to have told you that. Because, economists. Are there economists here? I'm really sorry. Sorry. Anyways, but this is what they do. And this is, you can quibble with the dates, but this is essentially kind of what we think. And what do you notice if you look at this chart? Okay, the colors actually kind of capture something, right? If you look at any of those pinkish red zones, they're broadly a lot more wobbly, right? There's a lot more going on there. And that's this idea that if you know the stock market, it goes up really slowly and it goes down really quickly. And that's essentially what the sort of dynamics you see here. So you could build these really complicated models that try to capture this sort of behavior, and trust me, economists do, but there's an easier way to talk about it, and that's just to build two simpler models. And then, stitch them together somehow. So this talk is really about that stitching process. Okay, so this is about as mathy as I'm going to be, the next two slides. So what is a hidden Markov model? It's a way of trying to capture complex dynamics, mostly, with some sort of simpler underlying structure. Suppose we have something we observe. Doesn't matter what it is, but it's complicated. We can build a complex model, but again, that's hard. So what do? We assume there's something else. We assume that there is some unobserved thing. I'm going to call it X. The thing I see is Y, but the letters don't really matter. And that's really where the structure is, right? There are arrows connecting these, right? So the things that we actually observe don't directly impact each other. They're sort of moderated by something else, some unobserved state. And this, because we don't actually see it, we kind of get to make it up, we can impose arguably unrealistic, certainly simple dynamics on it. You can call it Markovian, right? Markov processes are incredibly well understood, they're powerful, we like to chain them together in this room, and that was a joke, it's just one process, but yeah. But, we can work with them really, really well. Formally, the math looks like this. And what's really the key? It's this sort of just mathematical sweet spot between tractability and simplicity coming from this Markov assumption, and then really good expressive power and interpretation, as you'll see in a minute, coming from this sort of fact that we get to see a function of it. And when you say a function of something, that can be really, really general. And what's important is, even though the underlying thing is simple, what you observe doesn't have to be so simple. It doesn't have to be Markovian. And of course, you can always stick these in sort of more complex models. And this is really why they're such a good tool. One example from sort of my own world that I really like, this is my office mate's most recent paper. This is a brain, this is sort of a neurological task. And what they do is they stick somebody in a machine and say, look at this wall. And sometimes we're going to put a picture of a cat on it, and sometimes we're not. And the idea is that your brain is going to evolve, and it's going to do a bunch of stuff. We know a lot about how brains work. But ultimately, there will be sort of two states of dynamics. Your brain when it thinks about cats, and otherwise. And because people are slow and they get bored, there's not exactly a one-to-one mapping between cat seeing and cat thinking. So what you can infer here, you actually sort of get these two states probabilistically. What is the probability that you're correctly thinking about a cat then versus you're thinking about something else? So these are two states. You can see, it tracks the reality, or you're actually being shown a cat pretty well, and you actually observe sort of two different functional networks in a brain. And these are indicative of different thought processes. So it's just a really cool sort of building block. And it's just this tiny little part, right? This is the hidden Markov model that picks a different distribution over the space of graphs, that is an inverse covariance for a multinormal that gets wrapped up with brain stuff, right? It's a very small part, but it's incredibly expressive. It captures this whole idea of paying attention and getting distracted. So what is Bayesian inference, right? Bayesian inference is really easy. I'm putting that in quotes, right? You just write down a prior and a likelihood. Stan happens by like waking Michael Betancourt up and making him do a bunch of math for you in the middle of the night. And then you get to do posterior inference, and it's super easy. This is not necessarily true, right? Difficulty here is in the likelihood. You actually get, right, there's that X process. So there's a bunch of things, you don't see any of them. They're typically categorical, which is kind of iffy. These models, they're really nice, but the likelihood is this awful, like, integral over product terribleness. And in general, they're really hard to work with. There are two cases that are really popular and really easy to work with. And for most people, that's actually what just defines a hidden Markov model. First one is everything is linear and Gaussian. That makes statistics happy, because it always makes statistics happy. You get something also called a state space model, Kalman filtering. It's one special case of this framework. The other one is when this thing is finite, right? Integral is hard, small finite sums pretty easy for computers. And so that's the other case you can sort of approach correctly. So this seems intractable, but there is a hope. There's a bunch of bad jokes, I'm sorry, coming up. Right, there's something called a forward algorithm. This is a very clever algorithm from back in the 60s when people were really intense and thought hard about these things, to calculate the likelihood in a tractable way. It's a dynamic programming algorithm. It sort of makes everything linear in the number of time steps instead of exponential. Right, this integral and product thing doesn't blow out on you. It's incredibly clever. And really, what is the trick? It's that magic Markovian simple structure. Sort of means you don't have to do your full recursion. Just little small incremental steps matching the probabilistic structure keep things tractable. I'm going to speed up a little bit and blow through a few more things. Essentially, you just sort of, for each state, look at everything else. That's k squared, and then you just roll it forward to get something that's linear in your time steps. People have studied these a lot. There's a bunch of algorithms doing all sorts of clever things. Only one we're going to need for Bayesian inference is really just the log likelihood, which is the last one on this chart. These are all spelled out in some detail in the sort of paper that goes with this talk, but no one wants to hear an algorithms talk. So what happens? Once you have got your likelihood written down, the posterior strikes back, and life is not that easy. As much as I wish it would be. Two things always happen in these models, sort of a multimodality issue. There are a lot, which is bumpy and hard to sample. And then identifiability, strong identifiability, when you can make it, sort of a symmetry breaking through some sort of type system thing is really, really useful. In practice, can't always have it. Unordered things like the space of graphs I was talking about earlier lead you to just sort of a weak identifiability that you inherit from a prior. Same thing, multimodality. There are sort of these semi-supervised methods, like I was talking about, where you have a hint of what it should be because you have an external stimulus, or strong priors. But together, these things can really get through most of your problems. These are Ewoks. They have nothing to do with the talk. I just included them. They're non-Bayesian Ewoks, though. That's, because they're stupid. So here's just a finance example. Just blowing through this really, really quickly. This is this chart I showed you earlier. These are my two states, and I want to model this. So what can I do? Well, I'm a finance guy. The answer to everything in finance is to use a GARCH process, which is just sort of a time-varying volatility model for stock returns. This is incredibly popular. If you know finance, you've seen these 1,000 times. So what are we going to do? We're actually going to switch between two GARCH processes. We've got our good day GARCH, our sort of nice, slow uptick in returns, and then we've got our bad day GARCH, which is when the world goes to pot and everything's terrible. And how are we going to switch between them? We're going to follow a hidden Markov process. So again, what's going on here? We're actually using the hidden Markov process to pick which of these states we're in. From those states, we sort of evolve something else, and that ultimately generates our observable, our daily return. Here's the math, sort of. Code for it, this is not the best code. This is actually very simple code, but it's supposed to be very simple code, just illustrative purposes. This is the top half, I guess, of GARCH code. If you've seen this, this is very, very much like what sort of the Stanual looks like. I'm going to blow through it. And then this is the hidden Markov process. You'll notice this is all actually happening sort of upstream of your model. You do this simple, but takes a bit of space to spell it out, transformation of the parameters, and you get something that is your log likelihood. Just pretty much toss that in your model block and sample away. Right, what you actually see going on here is that you're sort of updating. It's that roll forward through time. This feels very natural and sort of very Bayesian, right? You know something, you see something new, you update what you think. You see something new, you update what you think. This is just sort of spelling it out algorithmically. And what comes out? Actually pretty compelling results. These are the two processes at each point. If you sort of look on average, the red process, the bad time, is generally about 3 times higher than the green, the good process. This is about what we see in the market. It's pretty accurate, predicts pretty well. This is the switching, sort of at each point, the probability that it was in a recession or not. You'll notice it is a lot softer than what you get from the Committee of Economists, but it skews to most of the time the world is not on fire, which is correct. Is this worthwhile? This is actually not my work. I was actually really pleased to see this. This is from sort of a non-Bayesian group who did a very similar model, and more power to them. They made a table of how much better their model was than the Bayesian model, and you'll notice pretty much every number on this chart is negative. So I actually have a lot of respect for that in terms of academic honesty. But that's point is, don't take my word for it. Take an admission against interest, to use a lawyer term. Anyways, and then here's the sad non-Bayesian Ewok. So I think I'm right under time. Funding, NSF, Google funded me, Google funded Luis, and really all power to the Stan manual that spells all this stuff out really nicely and should be absolutely your first stop in using these structures if they're at all of interest to you. Thank you.
Any questions?
Uh-oh.
Let's not see the same hands all the time. Does anybody else want to go?
So yeah, I wrote most of the HMM stuff because I used to do natural language processing. I've used them in a lot of examples though where you don't have the normality assumption. So I was wondering why you thought that was important.
So, I mean, it is not important for the finite state case, right? It's just when you have that god-awful likelihood, which is somewhere in here. This thing, right, there are two ways to make this tractable. Either stick a lot of linear Gaussians in here, and that gives you sort of very classic Kalman filtering stuff, or make it finite, right? It's an either or. But if you have nonlinearity and really big stuff you need, you have no chance of exact tractability. You've got to go like the linear Kalman filter, or the local stuff, or like the approximate stuff, right? There's a ton of these, but like, if you want exact inference, I guess you've got to have one or the other.
Well, I mean, you can do the MCMC without exact inference. So, like, one of the things I fit is like the movement HMMs,
Yeah.
where the output's two variables. One's a circular statistic, one's a positive constrained variable. Neither of them are normal, right? It fits fine under simulated data, real data.
Yeah, but right, you do it. You are taking that like, is that I'm done?
No, keep going.
Okay, right, yeah, absolutely, and approximations can work really, really well. And there's a
Well, I mean, this
you
is
don't
only
have-
an approximation in the sense of MCMC, right? It's not, you're writing down the actual log density for the model, right? So you can't marginalize it all out like in a Kalman filter,
Yes. Okay.
right? So
That's
we can't
fair.
do it super efficiently. We have to do it with MCMC in the end, but it's not an approximation in another sense.
Okay.
But anyway, maybe we can take this offline.
Yeah,
and
let's
discuss
do it offline. Anything else? Hit me up after if you want to talk more about this stuff. I think it's good. Or if you want to hire Luis because he's excellent.
I just wanted to ask about the multimodality problem. I didn't catch how you solved that.
Essentially, it's not quite label switching, but it's something close to it. Right? If you have these states that you truly know nothing about and have no reason to favor one or the other, you can swap them back and forth. So that's actually the identifiability problem, but a weaker version of that is modality. Right? You can switch some of the labels in part of it, and it's going to look very, very much the same. Does that make sense? It's multimodal posteriors in any sense of the way. Not in the linear Gaussian case again, not in any sort of like special case, but broadly just any other time you have a multimodal posterior because there's some lack of informativeness, you've got to put priors on it to make it sample decently. Essentially just if you have a hump of sort of probability mass here, a small hump all the way over here, it's really, really hard to get over here, right? And that's going to mess up sampling in various ways. So that's just multimodality in general. And that just comes from the fact that there's so many swappable components to these models.
Anyone else? All right. Thank you very much.